Now, let us see what smoke can do. Smoke effects. As the fire grows in size, that is, a commodity itself is burning, the extent of the fire increasing, and the heat release is increasing. Okay, it increases and becomes constant basically after a particular spread period. So, as the fire grows in size, more and more smoke hits the ceiling, and basically the smoke layer accumulates, that is, it comes down, the smoke layer thickness will increase, the smoke layer descends, and also, since the heat release rate is increasing, the temperature of the smoke layer will also increase. The smoke layer movement is caused by the air entrainment arising due to temperature gradient, that is buoyancy forces, between the hot gases and the surrounding cold air. Okay, so this smoke layer, because of the fact that the smoke cannot escape from the top part, it has to descend down, find a window or any opening, and then it goes out. So, if you go back to the pictures here, you can see that the smoke layer in this becomes more, first a grey type of smoke is there, it becomes darker and more darker. Now, here you can see that the smoke layer descends down. After this, you can see that from this it has come down. This is the more and more accumulation of smoke occurs, and there is no way it can go out. Probably something is going out from the front side, but the smoke layer descends down because of a larger heating rate here, heat release rate here, and the temperature also increases in this. So, this basically causes ignition of the other commodities. Okay. Now, smoke layer affects the visibility. We already seen in the pictures, correct? Once the smoke layer becomes more and more darker, it actually affects the visibility. Growth stage in the compartment fire is significant from a perspective of smoke movement. Okay, because initially the linear growth is seen. Once the smoke layer accumulates, radiative heat transfer from the smoke layer to the commodities occur, so that the heat release rate increases. Then a critical condition of flashover also occurs. So, that means the growth stage, how fast you reach the critical condition. We go to the graph, growth stage finishes here, where the critical condition is reached. Okay, now how fast you reach this, what is the time period for reaching this condition is dependent on the smoke layer movement. Well within the growth of the fire, okay, that is before the critical condition or flash over condition is reached, that is initial stage, we can say, the fire should be detected and safe egress, that is removal of people, should be carried out. Then in this small growth, okay, for example, within this period, say the temperature is not very high, well within say 500 degrees centigrade, etc., structure will not be so much affected. But if you allow it to grow for some more time, which can cause critical condition, then abrupt increase in the temperature will occur, which will cause the structural failure. So, structural failure should be avoided. That means you have to extinguish the fire within the, or at least cool the fire within the particular time, so that we can find some means to extinguish the fire. So, schematically the smoke movement is shown here. So, let us say there is a compartment and there is only one door here, this is the door. Okay. Now, there is some air is there in the compartment, and a particular commodity, say like a dustbin, etc., is burning, so that a flame is formed. The red color thing is the flame, and the plume is now growing slowly. The first stage. The second stage, the fire is established to some particular height. The plume grows and hits the ceiling. Okay, now ceiling jet is formed. that is it turns and sealing jet is formed. And now the third stage, the third condition, you can say the the flame is oscillating or it's still growing, and now we can see that the plume has hit the ceiling and a well established sealing jet is also seen, but there is no way the smoke layer here can go away because this is wall again, it has come down. So you can see that due to this fire there will be some outward movement of the gases in these stages. Now what happens is the fire is still burning, maybe the fire has reached the steady heat release condition, but the smoke layer is still descending. Now you can see the dynamics here, lot of recirculation zones etc. form and the smoke layer descends. Finally it descends to a particular stage where it is just above the door through which it can go away. Okay, now this in these stages you can see that the smoke layer temperature also increases, T of the smoke layer also increases as the smoke layer descends. Okay, now this is the condition, F is the condition where you will see a developed fire. Basically all the commodities will be burning at this time and the smoke now goes out. Now you can see that after the smoke engulfs to this point, there will be no oxygen which is left in. Probably what happens is the smoke goes out and there will be a formation of a plane. Under this plane there will be air which is coming in from the ambient, but over this plane I will see the smoke going out. So this is actually called neutral plane. We will see about this later. So these are the stages. Based upon the location of the vent or the opening, you will see different dynamics. Suppose if there is a window in this stage here, okay, then the smoke can go out of the window basically. It need not descend down so much. After it comes to a particular position, it may go out like this and the air can come in like this, etc. That is possible. But based upon the ventilation conditions what you provide, you will see that the fire dynamics within an enclosure can be entirely different. So this schematic shows the growth stage of the fire, okay, and from the ignition point to the fully developed fire stage. Now we talk about flashover where the critical condition has reached. So if you go back to the diagram, this diagram, initially the growth rate is slow in this, then the growth rate increases and reaches a condition where all the commodities are ignited at this point. Then there is a very rapid increase, you can see almost vertical it increases and goes to the stage of fully developed fire. Now the flash over is a condition where a very rapid increase is obtained for the heat release and the temperature. So transition of the fire from a single object which has started to burn in the compartment to sudden growth to its biggest possible size, that is called flashover. So if initially a single object is burning, you may not, if you don't control it, then it may ignite other commodities after its growth to some stage, where you will see that will be the biggest possible fire in the enclosure. So when the single component is burning, single commodity is burning or single object is burning, you will see that there will be not much effect. But once all the commodities in the room burn, that will lead to the formation of the biggest possible fire. So that is actually termed as flashover. So you can see in the figure, this is the flashover condition where all the commodities burn, lot of fuel gases are generated, no much the entrainment rate of oxygen is not very high. So it actually, because now the gases also will come out from this, okay, you cannot even visualize it, but the flame actually is seen outside the compartment, because it needs the fuel vapors which are generated, fuel gases which are generated needs more air to burn. That is the maximum possible fire size in the flashover condition. Now, flashover basically can be seen as thermal instability phenomena between the growth stage and the fully developed fire. Growth stage, something is growing initially linearly, then non-linearly, but a rapid increase occurs to the fully developed stage. Okay. In the graph, you can see that if, see for example, if the flashover doesn't occur, fully and slowly it is basically going to the fully developed condition like this, where all the commodities are burning. Fully developed fire is one where all the commodities are burning. So you can see that if the flashover doesn't occur, then what it means, all the commodities are ignited at a particular time itself, and slowly the fire grows. Or we can say that this sudden transition is not there. Maybe you put some controls to do this. Okay, anyway, we expect the fire to grow like this, but it has grown like this. That is the thing. Within a short time, I want to reach the fully developed fire at a particular time instant, say here, but I achieve that here itself. So that is this is due to some instability. Basically what happens is, multiple modes of heat transfer contribute to ignition of several commodities in the compartment. Okay, now sudden change in the slope of the temperature of the fire release, heat release rate, that is the indication of the flashover. Now, flashover, there are several definitions which are found in literature. That is, we have now just told that a rapid increase in the heat release rate or temperature can be told as the onset of flashover. Sometimes we can say that if the temperature of the compartment reaches beyond 500 to 600 degrees centigrade, then the radiation to the floor from the smoke layer will be around 15 to 20 kilowatt per meter square. The radiation heat flux can be in the range of 15 to 20 kilowatt per meter square. Now, what happens is the flashover will occur, we can say. So, there are several things. We can say that the sudden heat release rate increase or temperature increase can be the indication for this flashover, or the compartment temperature itself reaching about 600 degrees plus this indication of flashover, or if you see flames coming out of the opening, that is also indication of flashover, etc. Okay. Now, the flashover itself is the critical condition. We can't just see whether all the commodities are ignited, but the fire heat release rate is such that you can see very, very intense fire occurring in the compartment after the flashover. Then the flashover will grow to a fully developed fire. Developing fire grows to fully developed fire, crossing the flashover condition. So, let us see the features of fully developed fire now. So, after the flashover, a rapid increase in the heat release rate and temperature occurs, which leads to a fully developed fire. And this fully developed fire, go back and see this, the constant temperature is there, almost a constant temperature, because everything is burning at a steady state until the 80-90% of the commodities are consumed, then the decay starts. So, this stage is called fully developed fire. Here, as we saw in the graph, this period is the longest period because it burns all the commodities, and the burning rate is also constant, etc. So, heat release rate also is constant, and at the most dominant stage, because already we have come to the maximum burning condition. So, you need information about this stage. That is, if you have a compartment with several commodities, you know what is the fuel load in that. Based upon the fuel load, you will know what is the time when all the commodities burn, what will be the time required for burning that. You know the flammable characteristics of these materials. Then using this as the basis, we can design the fire protection of the buildings. Okay, so basically what happens is, you have a fire. If unfortunately we are not able to extinguish the fire within the critical condition, then the flashover occurs and we go to the fully developed fire stage. And now is the condition which will appear at this fully developed stage will be affecting the structure. That is, the structure can fail now. Okay, so this growth stage, flashover conditions and the fully developed stage have to be analyzed properly. In this stage, basically we can define or quantify the fire boundary condition, whether the fire will lead to propagation from one room to other. Okay, then the temperature increase in the room will be such that the thermal response of the structure or structural response of structure will be affected or not. So, let us understand the thermal response of the structure. Thermal response is, if there is a structure at say ambient temperature 30 degrees centigrade, it has some strength, toughness, etc. Now, when the structure is heated up, its strength decreases. So, thermal response of the structure is, if the structure is heated up, how the strength decreases. Now, this structure normally will be connected to other structures. For example, a column will be connected to a beam and so on. When the connected structure, for example, is heated up, then that will affect the structural response of the structure, but the column may not hold the beam and so on. So, these will affect the evacuation protocol, correct. Even though we are trying to evacuate the people well before the critical condition is reached, in sometimes structural failure can occur and some evacuation protocol can be under this. We cannot actually complete the evacuation within the required time in some cases. So, for this we should understand the fully developed fire stage. Now, based on the ventilation conditions, the fully developed fire can be categorized into two regimes. Okay, now first one is called ventilation controlled or regime 1. Second one is called the fuel control or regime 2. So, all the commodities in the room is burning. If there is only limited ventilation or ventilation is good enough, say there are some 2 or 3 windows and door is also open, etc. So, there are several scenarios. As we saw in the photographs, you can see that the front portion of the compartment itself is open, so that you can see that the flame coming out, etc. When will be these two regimes are observed? We will see that in the ventilation control, fire is oxygen starved, that is, ventilation is limited, maybe only one window is open, lot of commodities are burning. You will see that more air is required to burn them. That is, the fire is fuel rich and oxygen starved. It is just burning with available oxygen, but more oxygen is required. Okay, smoke flowing out of the compartment has no oxygen, etc., because only fuel rich gases which need more oxygen flow out in this stage. That means these gases will burn outside the enclosure. So, go back to this stage. As I told you, in all the commodities are burning, not enough entrainment of oxygen occurs. Even though the ventilation is such as this, you can see that all the commodities are burning, oxygen supplied to all this is not enough. So, fuel rich hot gases go out, and now they are hot also mixed with oxygen from the outside the compartment. So, flame is formed outside the compartment. This is ventilation control. Second regime. Okay, now in the first regime, ventilation conditions are such that the air entrainment is lesser than that required for the fuel to burn within the compartment. That is the first. Second regime is ventilation is good, but there is no much fuel to burn. Fire is fuel starved. Here, the smoke coming out of the compartment will have good amount of oxygen. A lot of oxygen has entrained, but there is no much fuel, or all the fuel is burning within the compartment. So, you may see some CO2, H2O, N2, O2 etc. in the gas, a little amount of CO also can be there. So, that is the regime 2. But here the fire will continue only until the fuel is left over. Okay, that is the second regime. Now, in both the conditions, you will see that the heat release after reaching the fully developed stage, constant stage, it decays. The natural decay of the fire occurs due to lack of fuel, that is, fuel availability is less or lack of oxygen. When oxygen cannot entrain more, the decay will occur. What is artificial decay? I detect the fire and suppress it, say using sprinklers or any other agent. That is artificial decay. So, fully developed fire categorized into two regimes: ventilation controlled and fuel controlled regimes are seen based upon amount of oxygen available for the fire within the compartment. The heat release rate during the decay stage reduces rapidly. Again, go back to the here. After the fully developed fire, a decay stage, you can see the rapid decrease in the heat release rate. Average temperature also decreases. Obviously, when heat release reduces, obviously the average temperature also will reduce. A value of 80% of the peak temperature is used to identify the decay. So, you see that the compartment is burning, temperature is of the smoke layers etc. will be about 800 or 900 degrees centigrade. But now, how will you find the decay stage has started? When the temperature decreases from 800 to 80% of that value. Okay, or we can also say that the decay has started and now it will rapidly decrease. Now, for most structures, temperature decays at a rate of 5 degrees centigrade per minute. Okay, a structure is now heated due to the fire. A structure is heated, maybe steel structure or concrete structure etc. is heated. Now, fire may decay at a very fast rate, but the temperature decrease in a structure will not be at that rate. It may be just 5 degree centigrade per minute. So, it will be slowly, unless otherwise it is actually cooled by spraying water or any other thing. So, we have now understood about all the stages. Basically, the fully developed stage, which is the constant burning period, then the decay stage etc. And in the fully developed stage, we have two important aspects. One is, in some cases due to poor ventilation, we can see that the fire will be oxygen starved, and in some cases where lot of oxygen can entrain into the compartment, the fire will be fuel starved. Now, we will talk something about duration and severity of the compartment fires. These are the two main components to understand the fire behavior, especially when the fully developed fire has occurred. So, as I told you, you first need fuel load, that is the total mass of fuel available for burning, and there are several commodities. Each commodity can burn with its own burning rate. Steady burning rate, when you say burning rate of the fuel, it is the steady burning rate. Once the flame is formed over the material, it consumes the material. That burning rate we are talking about here. So, duration, again if you go back to the, this is what I am fully developed fire duration. This is the maximum duration also, the longest period of burning. So, this duration, because it actually consumes the material not at a very high rate. So, duration is defined as the burning rate of the fuel into total mass of the fuel which is available. Now, severity is quantified by the maximum temperature of the compartment. Okay, because the temperature, see, some fire can lead to a growth of smoke layer and the smoke layer reaching a temperature of 800 degrees, etc. But in some cases, you can see that when energetic this materials burn, you can see that the temperature can also exceed the values of 800, may reach 1000, etc. So, the severity of the fire is basically determined by the maximum temperature attained in the compartment, which is basically going to cause structural failure, because when the temperature is higher, then the structure will be heated up, but structure will not lose the heat as soon as the fire decays. So, that is the reason where we need to worry about the maximum compartment temperature. Now, there is a difference between a fire in an open condition. If, for example, in a open field, I have a burning of some commodities, but the same commodity burns within a compartment, the features will be entirely different. So, the meaning of this is, when you do some tests to determine the burning rate of the fuel, the burning rate can be dependent on the enclosure effects. So, when a particular fuel, solid fuel or liquid fuel, any other fuel burns in open environment, it may have a certain burning rate, but the same fuel, if it burns within the enclosure, the burning rate may be different. So, the difference between the fire burning in open or within a compartment has to be made. That means some flammability characteristics of enclosure burning has to be determined. For that, already we have told that there are standards to create an enclosure and burn commodities in the enclosure to understand the burning behavior of the commodities within the enclosure. Now, when the fire is burning in open, the rate of burning induces the rate of air entrainment, because air is free to entrain. When the rate of burning increases, we will see that the buoyancy force also increases, because the temperature gradient increases, etc. So, due to this, the air entrainment will be increased. The strength of the fire will lead to more and more air entrainment. So, that means the air which is entraining can feed the flame or the fire, and the fire will grow correspondingly. But within a compartment, the rate of burning and the rate of air entrainment need to be considered in a different manner, that is separately it should be analyzed. Because, for example, there are regimes in fully developed fires. One may be in oxygen starved regime, how the burning will take place. In fuel starved regime, how the burning takes place. There are differences in this. So, we need to analyze them very carefully. Now, the graph shows two scenarios observed in compartment fire. Here, we can see that the temperature versus a factor which is called ventilation factor, where AT is the area of the enclosure without floor and openings. Now A0 is the area of all the openings alone. H0 is the height of the opening, each opening, for example. Now I create a factor like AT divided by root of A0 H0. That is called ventilation factor. Thomas and Heselden have given this plot where two regimes are explained. So ventilation factor basically can be considered as, that is, how much openings are there for air to enter in, etc., can be seen in the ventilation factor. So can be actually factored in this particular factor. Now let us take this. When you say the ventilation factor, the area of opening is in the denominator. That means higher the ventilation factor, the vent area or the air entertainment area actually decreases. Okay. So this arrow shows that the vent area increases from right to left. Okay. So when, let us go to regime 2, fuel starved condition, because in this regime the ventilation area is higher, lot of oxygen can be there within the compartment. So what happens in this regime? So start from particular point here, then as the ventilation increases, the temperature drops because of more and more air. Air means nitrogen also comes in. So this is the regime 2, where the fuel is starved, oxygen is plenty. Now you go to other here, when you go from this point towards the right, as this ventilation factor increases, then what happens is there is a decrease in temperature again. Why? Because the burning rate decreases because of the reduction in the vent area when you go from this point to the right here. Okay, so these are the two regimes basically. Now in this, data from several experiments have been included. For example, if you take, say, this open rhombus or fully shaded rhombus, then squares, circles, etc., the symbols of different shapes represent different vent shapes. Then the numbers here 40, 30, 20, etc., numbers represent the fuel load density, that is kg per area meter square. So we can see that the effect of ventilation is very severe, or it affects the temperature distribution or heat release also correspondingly. In this, the two regimes can be identified. When the vent area increases, larger vent area, you can see that there is a decrease in temperature as the vent area increases. In the fuel, this is actually fuel lean condition, the fuel rich condition. That means the oxygen entrainment rate is not very high, especially when you decrease the vent area, when you go from this point towards the right, and you can see the burning rate or the temperature rise decreases, because the heat release also decreases in this. Okay. So these are the two important regimes which actually seem to be affected by the vent shapes, fuel load, as well as the oxygen entrainment.